Hey everyone, and welcome to this explainer. Today, we're doing something really cool. We are stepping into the role of translators. Now, we all know artificial intelligence is completely revolutionizing how we discover new drugs, how we design advanced materials, basically how we understand the physical universe. But before AI can do any of that, we have to bridge this massive gap between human science and computer processors. We literally have to translate chemistry into a language that AI can actually understand.
So let's dive right into the core problem. How do you actually teach a machine to understand chemistry? Because think about it. You and I look at chemistry as physical shapes, right? Reactions, bonds, 3D space. If I ask you to imagine a water molecule, you're probably picturing that classic Mickey Mouse shape, an oxygen atom hooked up to two hydrogens. But computers, they don't have eyes. They don't have a physical imagination. They only speak one language, and that's math. Numbers and symbols. So if we want AI to invent the next life-saving medicine, we absolutely have to translate those physical shapes into pure data.
All right, here's our game plan for today's explainer. We're going to start with the chemical language barrier, move on to translating molecules for AI, check out descriptors and molecular barcodes, then sourcing chemical data, and finally, we'll wrap up with prepping and cleaning data. Okay, let's jump right into part one, the chemical language barrier. This is the literal disconnect between the wet lab and the computer processor. Just look at the massive difference here. On the left, we've got the human view. We naturally think in terms of structural formulas. You know, if a chemist wants to represent ethanol, they'll sketch out the carbon, hydrogen, and oxygen atoms, draw the lines for the bonds. It's super intuitive for us. But check out the right side. The computer view is completely different. It requires numbers, symbols, mathematical representations. You can't just take a JPEG of a molecular drawing, feed it into a standard machine learning model, and expect it to do anything useful. Without converting that drawing into math, training an AI is just a non-starter. And hey, it's not just about the physical shape of the molecule either. It's about how it behaves in the real world. We're talking physical properties here: molecular weight, melting point, solubility. This right here, this is the absolute goldmine for AI. What machine learning models are actually doing is figuring out the hidden relationships between a molecule's mathematical structure and these real-world measured properties. Because once the AI cracks that code, it can start predicting the melting point or solubility of brand new molecules that no one has even synthesized yet, which is just wild to think about.
That brings us to section 2, translating molecules for AI. Let's look at the actual tools we use to turn physical chemistry into machine code. So how do we actually do this? Well, we give the computer an alphabet it can read. Take common molecules like methane, ethanol, acetic acid, benzene. Methane simply translates to a capital C, ethanol becomes CCO, benzene becomes this string of lowercase c's and numbers. We are literally taking complex three-dimensional structures and squashing them down into a single flat line of text. We call those text strings SMILES, which is honestly a great acronym. It stands for Simplified Molecular Input Line Entry System, and it's easily one of the most important translation tools in AI chemistry today. Why? Because it's incredibly compact and completely computer readable. Think about something complex, like aspirin. Instead of storing a heavy image file of aspirin structure, the AI just stores a tiny string of text. And modern AI models treat these SMILE strings exactly like human language. Just like a chatbot predicts the next word in a sentence, a chemical AI can predict the next atom in a molecule.
But beyond SMILES, there's another crucial standard we rely on called InChI, or the International Chemical Identifier. Now, SMILES is fantastic for training models, but a single molecule can actually be written in a few different SMILES formats depending on which atom you start with. InChI fixes that. It provides a globally recognized, totally unique identifier for every single molecule out there. It's basically a chemical fingerprint that guarantees databases around the world stay consistent, so our AI doesn't get tripped up by duplicates.
Actually, scratch the text strings for a second, because that's not the only way to translate. We can also use molecular graphs. This is where atoms become nodes and bonds become edges, and this introduces us to a massive breakthrough: graph neural networks, or GNNs. So instead of forcing the AI to read a flat line of text, GNNs let the AI learn directly from the molecule's structural shape. By looking at the molecule as a network, the AI perfectly captures how those atoms interact in space. For advanced stuff like drug discovery and toxicity prediction, GNNs are an absolute game changer. All right, so we've got our structural language down. Let's move to section 3, descriptors and molecular barcodes. This is how we build out the machine's numerical vocabulary. Because here's the thing, even if you give an AI a neat SMILES string or a complex graph, underneath the hood, that machine learning model still needs to chew on cold, hard numbers. We call these numbers molecular descriptors.
A descriptor is just a specific numerical trait. Molecular weight is the total mass. Atom count is, well, exactly what it sounds like. Then you have things like log P, which measures lipophilicity, basically how well a molecule dissolves in fats. These descriptors are the actual input features the AI learns from. We're just breaking the molecule down into a stat sheet.
And if we take those descriptors one step further, we get molecular fingerprints. Just like a human fingerprint uniquely identifies you, this identifies a chemical. But look at it. It looks like a barcode, right? Just a long string of ones and zeros. A fingerprint can contain hundreds, sometimes thousands of these binary values. And every single position in that barcode is just answering a simple yes or no question. Is this specific structural feature present? A 1 is yes, a 0 is no. This clever setup lets AI rip through millions of compounds, running similarity searches in literally a fraction of a second.
Which leads us perfectly into Section 4, sourcing chemical data. Because to train a truly great AI, you need a massive library of this translated data. So where on earth do we get it all?
The answer? Massive public databases. These are the absolute heavy hitters of AI chemistry. You've got PubChem, which holds millions of compounds and biological activities. ChEMBL, which zeroes in on drug-like molecules and pharmacological data. The Protein Data Bank is incredibly vital if you're doing AI-driven drug design. Then there's ChemSpider for spectral data, and the Materials Project for anyone using AI to hunt down the next generation of batteries or semiconductors. These databases are literally the fuel running the entire AI chemistry engine.
So, when a team actually sits down to build an AI project, they generally follow a strict 4-step workflow. First, define the objective. Like, say we want to predict water solubility. Second, collect the molecules from those databases we just talked about. Third, gather the actual experimental measurements for those specific molecules. And finally, step 4, store all of that in a machine-readable tabular format. It just takes this massive abstract goal and turns it into a tangible, organized process.
But as any data scientist will tell you, just gathering the data isn't enough. That brings us to Section 5, prepping and cleaning data. This is where we proofread our translated text so the AI doesn't learn the wrong lessons.
Before we feed anything to an AI, it has to be perfectly structured. Look at this table. We have our molecules, A, B, and C. We've got our input features, like molecular weight and log P. And crucially, over on the right, we have our target outcome, solubility. Keeping this clean separation between the features we know and the target we want the AI to predict is the absolute foundation of supervised machine learning.
But let's be real. Real-world data is almost never this pretty. It requires rigorous cleaning. You've got to handle missing values, either scrub the record entirely or safely estimate it. You absolutely must remove duplicate records or you're going to bias your model. You have to standardize your units. I mean, if one lab measures in Celsius and another in Kelvin, the AI is going to be hopelessly confused. And we have to normalize the data scale, so a massive number like molecular weight doesn't completely drown out a tiny number like a log P value.
Then, once the data is flawlessly clean, we split it up. The standard rule of thumb is 70-15-15. 70% of your dataset becomes the training set. This is what the AI is actually studying. 15% becomes the validation set, which acts like a practice quiz to tune the model's parameters and keep it on track. And that last 15%, that's the test set. It gets locked away until the very end. Think of it like the final exam, to evaluate how the AI performs in the real world on molecules it has literally never seen before. Even with all of that rigorous prep, we still face some pretty major hurdles. Data scarcity is huge. Some properties just haven't been tested much in the lab. Then there's experimental variability, where 2 different labs might test the exact same molecule and get slightly different results. Measurement noise introduces unavoidable errors, and data bias creeps in when our databases overrepresent certain types of easy-to-make molecules. Navigating these landmines is exactly why clever feature engineering and incredibly strict data practices are so vital. So that brings us to the ultimate question. We've seen exactly how we translate the messy physical world of atoms and bonds into the digital language of smile strings, graphs, and molecular barcodes. We know how to source the data, scrub it clean, and feed it into the machine. Honestly, it's a staggering achievement in science. So the takeaway I want to leave you with in this explainer is this. Now that we can successfully translate chemistry for computers, what new, world-changing molecules will AI discover next? The groundwork is completely laid. The language is spoken. Now the real discoveries begin. Thanks so much for joining me on this explainer, and keep that curiosity alive.